Hi guys, this is Grant Steinfeld from Big Code Heroes, and I'm here to talk to you about the actor model. So our CPUs are not getting any faster. What's happening is that we now have multiple cores on them. If we want to take advantage of all this hardware we have available now, we need a way to run our code concurrently. Decades of untraceable bugs and developers' depression have shown that threads are not the way to go. But fear not. There are great alternatives out there, and today I want to show you one of them, the actor model. The actor model is a conceptual model to deal with concurrent computation. It defines some general rules for how the system's components should behave and interact with each other. The most famous language that uses this model is Erlang, and I've used it before, and it really is great, and believe you me, it really does epitomize the actor model. So I'll try to focus more on the model itself and not how it's implemented in different languages or libraries. So what is an actor? Essentially, an actor is the primitive unit of computation. It's a thing that receives a message and does some kind of computation based on the receiving of that message. The idea is very similar to what we have in object-oriented languages. An object receives a message via a method call and does something depending on which message it receives, which method we are calling, or the callback. The main difference is that actors are completely isolated from each other and they will never share memory. It is also worth noting that an actor can maintain a private state that can never be changed directly by another actor. So here's an old adage, one ant is no ant. Similarly, one actor is no actor. And comparatively, if there was one human, there would be no society. So we wouldn't be able to communicate, and we'd sort of be useless, and it would be sad. So actors come in systems or ecosystems. And in the actor model, everything is an actor, and they need to have addresses. So one actor can send a message to another. Actors also interestingly have something called a mailbox. So this is like a queue, and this is where the messages come in, and if an actor is overwhelmed, the messages will queue up and will be processed sequentially. It's important to understand that although multiple actors can run at the same time, an actor will process a given message, as I said, in sequence. This means that if you send 3 messages to the same actor, it will just execute one at a time. To have these 3 messages being executed concurrently, you'll need to create 3 actors and send one message to each of the 3. Messages, as in the reactive manifesto, are sent asynchronously to an actor. That needs to store them somewhere while it's processing another message. The mailbox is the place where these messages are stored. So just to summarize, actors communicate with each other by sending asynchronous messages. Those messages are stored in actors' mailboxes until they are processed. So what happens when a message arrives? An actor can do one of 3 things. It could either create more actors, it could pass on the message and send it to another actor, or it can designate what to do with the next message. So actors can mutate and decide what to do when messages arrive. So it could either do a CRUD operation, it could do a lookup, or it could send it on to someone else. So actors are mutatable or mutable. I said before that an actor can maintain a private state. That is, it is isolation. No other actors can see what's going on inside another actor. Designating what to do with the next message basically means defining how the state will look like for the next message it receives. Or more clearly, again, I state, this is how actors mutate their state. Let's imagine for a minute we have an actor that behaves like a calculator, and that its initial state is simply the number 0. When this actor receives the add 1 message, function add, parameter 1, instead of mutating its original state, it designates that for the next message it receives, the state will be 1. Another aspect of actors is that it talks about fault tolerance. So Erlang introduced the let it crash philosophy. The idea that you shouldn't need to program defensively, trying to anticipate all the possible problems that could happen and find a way to handle them. It is with error handling, simply because there's no way to think about every single failure point. So we can't write try-catches all over the place. We have to sort of structure them and think about where failures may happen, and often than not, we don't catch some errors. So what Erlang does, and similarly so do actors, it simply lets it crash, but makes the critical code be supervised by someone whose only responsible is to know what to do when the crash happens, like resetting this unit of code to a stable state. And what makes it possible is the actor model. Every code runs inside a process. That is basically how Erlang calls its actors. This process or actor is completely isolated, meaning its state is not going to influence any other process. We have a supervisor that is basically another process or actor. Remember, everything is an actor. That will be notified when the supervised process crashes, and then it can do something about it. This makes it possible to create systems that are self-healing, meaning that if an actor gets an exceptional state and crashes, for whatever reason, a supervisor can do something about it and try to put it in a consistent state again. And there are multiple strategies to do that, the most common being just to restart the actor with its initial state. Distribution. Another interesting aspect of the actor model is that it doesn't matter if the actor that I'm sending a message to is running locally or in another node. This is location transparency. So the actor could be running locally on the same VM, on the same JVM, on the same Kubernetes pod, or it could be running completely in another server in the same data center, or even remotely in a remote data center on the other side of the planet. Think about it. If an actor is just this unit of code with a mailbox and an internal state, and it just responds to a message, who cares in which machine it's actually running? As long as we can make the message get there, we are fine. This allows us to create systems that leverage multiple computers and help us to recover if one of them fails. This was a quick overview of the conceptual model that is the base of great languages like Erlang and Elixir, and libraries like Akka for the JVM, and Celluloid written in Java. If I was successful in making you curious about how that model is implemented and used in the real world, there is further reading to be done, and we can discuss this. I would say there are 3 books worth looking at. There's 7 concurrency models in 7 weeks, When Threads Unravel, Programming in Elixir, and Elixir in Action. So there you go. That's Actors in a nutshell. It's a very fine framework. It was invented by Charles Hewitt back in 1977. So as you can see, like most software, a lot of the concepts we use today were actually thought about many years ago, and the full life cycle of these aspects come around again, and we see them happening in modern day systems, and that allows us to write extremely high frequency, low latency, fault tolerant, elastic message passing applications, which is exactly what the Reactive Manifesto talks about. So thanks for tuning in. I'm glad to talk to you about the actor model, and I look forward to presenting in my next podcast, Akka Streams. Okay, thanks and ciao.